Hi, everyone. Very good evening. Welcome to this CDSA webinar. So today we have an awesome guest speaker with us. We have with us Ishan. Just a brief intro about Ishan. Ishan is a research scientist at Meta, formerly Facebook AI in New York. He works on computer vision and machine learning with a focus on developing models that are flexible and learn without human supervision. He has published over 35 papers in top-tier computer vision and machine learning venues. Ishan received his PhD in robotics from CMU in 2018, where his thesis received the SCS Distinguished Dissertation Award. He was a runner-up for that award. Ishan has actually worked on some awesome papers and fascinating research problems, and we are so delighted to have Ishan with us. And as I think some housekeeping rules here. It's an hour-long session, and around 40-45 minutes, Ishan will dedicate to his talk. In between, if you have any questions, you can please put them in the chat window. And also the last 10-15 minutes, we can dedicate to any questions you have for Ishan. Without further ado, over to you, Ishan. Thanks again for accepting our invite and making time for us.
Thank you, Anuj. Thank you, everyone. So today I'm going to talk about machine learning, and with a focus on basically whether we can teach machines to see without really teaching them. So one of the sort of biggest success stories of AI, when you hear about AI doing like superhuman things, like becoming awesome at recognizing leaves or recognizing dogs or recognizing anything, has really been this paradigm of supervised learning. So most AI applications that you'll see around you are actually going to use some form of supervised learning. So image search, image tagging, recognizing objects, these are some sort of classical examples of using supervised learning for computer vision. So before we look into what are the sort of drawbacks of this approach, let's first try to understand what supervised learning is. So for supervised learning, we basically have an input, I, so in this case, an image, which we feed into a model. Say it can be a model called ConNet. And that model produces a confidence for 3 classes in this case. So it produces a confidence score for each of these classes, whether it's confident that this image has a table, a tree, or a dog. And in this case, the model thinks that this image has a table because it's producing the highest confidence score for a table. Now, of course, this is not right, but we want to teach this model. So to do that, we basically have someone label this image, and we get a label called tree. And now what we can do is, once we have this label, we will compute a loss that tries to maximize the confidence of the model's prediction for this label tree. And then that basically gives us a loss score. Once we do that, we can actually update the model. We can update its parameters so that the next time it sees this image, the confidence score that it produces for tree is actually the maximum. So in that case, basically all the wrong classes, which would be dog and table in this case, are suppressed, and the confidence score for the tree class is the highest. So most of supervised learning really assumes access to these input and labels. So this pairs of input I and label L. And the idea basically is that by giving a lot of these inputs and labels, you can train a very nice model that learns to recognize lots of concepts, lots of images, and so on. Now, this has been extremely successful, but there are certain bottlenecks in supervised learning. One of the biggest bottlenecks is really this supervision or getting access to labels. And as I'll try to show you in a few more slides, this is really, really difficult. So let's start with the thought experiment. Can we really get labels for all data? So to do that, I'll basically talk about whatever computer vision researchers have done, what sort of public data sets exist, and how their scale compares in the next few slides. So one of the important tasks in computer vision is basically not only recognizing what objects are present in an image, but also telling where they are present. And to do that, we basically want to draw boxes around all the objects of interest. So in this case, say we say that there is a dog, a chair, a pizza, and donut. We also want the machine learning model to draw boxes around where these concepts are present. And to do that, we of course need labels. We need someone to have told us where these objects are and basically also have labeled them in the particular image. And so if you look at all the sort of images that have bounding boxes, which are these kinds of annotations, we get about 1 million or so images by collecting together various different benchmarks from the world. Now, this may sound like a lot, but what happens if you were to relax this constraint? Because clearly drawing boxes is a cumbersome task. Someone needs to go and like basically use either their cursor and draw each of these boxes. It's of course going to be slightly easier to not have to draw these boxes and just tell the machine, these are the kinds of objects that are present in the image, and that's it. And so yes, we can actually relax that constraint and we can get labels which are just image level. So in this case, we will not have boxes, but just the concepts present in the image. And what ends up happening is we get an order of magnitude more data. So we'll actually get, in this case, 14 million images or so by collecting together a lot of benchmarks. Again, this may seem like a lot, but all of this kind of pales in comparison to the amount of images that exist on the internet. So if you look at the amount of images on the internet, this is an estimate from about 4 years ago, it's more than 1 trillion images on the internet. And so this is not an error in plotting. It's just that the bar graphs for bounding boxes and image level are so low that they don't even show up on the axis. So you'll have to move to like log scale on the y-axis to even see that these things exist. And you immediately see that there's a 6 orders of magnitude different between the image level data that we have and the internet photos that exist. And this is just internet photos. The real world has far too many concepts. If you think about all the kinds of data that exists, images, not only on the internet, but say medical images, videos, even like richer forms of data, 3D images, and so on. And to just throw another statistic there, the largest sort of data set for image classification called ImageNet has just 14 million images, and it needed 22 human years to label that particular data set with 22,000 categories. So clearly you can see that if we were to just to try to scale this kind of labeling to lots of concepts, lots of data, trillions of images, it's really not going to scale because all of this labeling is extremely cumbersome and extremely time consuming. So in general, labeling just does not scale to the size of data that we generate. It does not scale to the complex concepts, does not scale to something like video because now someone needs to like scroll through the video and annotate it. And this is one of the bigger problems of just acquiring data. Now, the second problem is that there are lots of rare concepts in the world. If you ask someone to go and label cars, you'll get lots of cars and that person can go and label cars, but you're naturally going to get fewer cars that are say turned upside down because that is a rare occurrence. But of course, you want your model to also recognize these kinds of rare occurrences of a car being upside down, or even rare concepts in the world, exotic fruits, for example, or exotic plants. And in general, this basically follows a Zipfian distribution, where the idea is that 10% of the classes, so 10% of the concepts in the world actually have 93% of the data. So if you were to collect 100 samples, you'll only get a very limited coverage of the amount of classes that, or the amount of concepts in the real world. And so even if we were to scale labeling, what ends up happening is that for these rare kind of concepts, we're going to acquire very, very few labels. So this is another sort of bigger bottleneck of just relying on some person to sort of label all these images. And finally, the other problem is getting labels can also be extremely difficult. For certain domains like medical imaging, not everyone can go and label these things. So you really have very few experts who are actually able to label these kinds of images. And so you're completely bottlenecked by the availability and the time of these experts who are going to go and label these domains. Now, if you think this is it, this is not it. There are actually multiple other limitations of supervised learning. So in 2019, we did a study where we took a lot of these commercial AI recognition models, which recognize images, and we basically applied them to a bunch of images from different parts of the world. And lo and behold, we found very, very interesting results. So in each of these 3 columns, we have the same concept, soap, spices, and toothpaste, but the images are coming from different parts of the world. In the top row, they're actually coming from the developing countries in the world. And in the bottom row, they're coming from the developed nations of the world. And in this case, what you immediately observe is that when the same concept occurs in a different part of the world, the prediction for the model is very, very different. So it thinks that soaps from Nepal are actually food, where it is actually able to recognize soaps in the UK really well. If it thinks that spices coming from Philippines are actually beer, and toothpaste coming from Burundi is actually wood. And when we aggregated these statistics all over the world, the accuracy of these models according to where the images are taken from we observed that basically the accuracy plot looks something like this. It's really, really high for all the developed nations, and it's really, really low for different parts of the world. And even more troubling was the fact that there was actually a correlation between the income of the household where that picture was taken and the accuracy of the model. So the models tend to work better for basically households with higher income. And really, a lot of this boiled down to how these models were trained. A lot of the data that is being used for training these commercial AI models comes from developed countries. And so they tend to basically not work for developing countries because they've never really sampled those concepts, never really seen those kinds of images. And so with these kinds of limitations of supervised learning, is there any alternative? Can we do better? That brings us to this concept called self-supervised learning. Self-supervised learning is a paradigm of machine learning that really does not require access to human labels to learn good visual concepts. So the key sort of idea in self-supervised learning is to use the data itself as a source of supervision. So suppose I have a lot of data. What I can do is I can split it up into two chunks. I can think of one part of the data as the observation, and then I can hide a certain other part of the data. And I can set up a prediction problem where I try to predict this hidden data from the observed data or some kind of hidden property of the data. And now in this case, I didn't really require anyone to label this data, right? All I did was just split up the data into two parts. So this is something that actually easily scales to lots of images, lots of data very, very easily. So let's take an example from natural language processing. You can actually solve this task called fill in the blanks. So you have a sentence, a cat jumped over the fence. And what you can do is you can basically just hide the word cat and feed the remainder of the sentence into the model and ask it to predict what do you think is actually going to be in this blank. And the model basically gives an answer. It can be cat or dog and so on. And then you basically just train the model. So in this case, the label is obtained automatically. No one had to go and label it. And in fact, this particular task of fill in the blanks is actually one of the biggest success stories of self-supervised learning in NLP. There was this very, very influential work called BERT from 2018, which shows that you can learn very powerful models by basically just solving this fill in the blanks task in natural language processing. So in this talk, I'm going to really focus on self-supervised learning, but in the context of computer vision, which focuses on visual data, so images, videos, 3D, and so on. And in this case, the two sort of really important properties that exist for any self-supervised model are multi-view invariance and grouping. So what does multi-view invariance mean? It means that if we were to recognize a tree, we should be able to recognize that tree no matter the weather, whether it's winter or whether it's summer, no matter the time of the day, no matter how we are looking at it. No, basically the same instance should be recognizable under different viewing conditions, under different weather conditions and so on. And the other is grouping. We should be able to say that a tree is related to another tree. And so that basically creates this concept of a tree, that basically all of these things that have a trunk, have leaves, are basically related to one another, and they are going to be trees. So to sort of quantify this a little bit, what we really want are, when we train this sort of machine learning model that takes input I, feeds it into a model, we want to look at the features of this machine learning model. So the last layer that I talked about when I introduced supervised learning, what we do is we take the connet and we make a prediction whether it's going to contain like a dog, a tree, or a table, and so on. But in this case, what we want is to basically look at the layer prior to that in a deep learning model and look at the output of that layer, which we can think of as its feature. And succinctly, we can think of it as a function, f theta, of the input image I, where theta are the parameters of the model. And what we want is basically f theta of I to have the properties that I mentioned earlier. It should have multi-view invariance, and it should be able to capture some notion of grouping. And essentially, since 2019 to even today, one of the key sort of success stories of using self-supervised learning in computer vision has been to learn features that are invariant to augmentation. What this means is that if I look at an image of a deer on the top left, I can apply various different image editing or augmentations to it. So I can change its color, I can crop it, I can zoom into it, I can rotate it a little bit, and I can do any of these operations in combinations as well. And in each of these cases, what we want is f theta of I, the feature that we extracted from the original image, should be the same as f theta extracted from any of these augmented or image edited versions of the image. And we really want to just enforce this condition. And it turns out that by enforcing this condition and a few others, we can learn extremely powerful feature representations of the visual world. So how do we operationalize this insight? What we do is we basically take an input image, we apply two different augmentations to it. So you can think of these as image editing. We feed them through a model, again, a connet in this case, and we just compute a loss that enforces that the features from these two different augmented versions are essentially the same. So the features are going to be unchanged no matter the input augmentation. And most of the work that has come out in the past 3 to 4 years has really focused on learning these kinds of invariant features. And a lot of the sort of technical innovation in this area has been in designing nicer sort of loss functions to basically enforce this kind of constraint. And of course, the constraint that I met earlier is not, it's a necessary constraint, but it's not sufficient because you can have invariant features, but they can be completely useless for recognition. So there are some kind of like trivial solutions or some kind of bad solutions when you enforce that. So most of the innovations in this area have really been around how to prevent those kinds of trivial solutions while being able to learn very important invariant features. So I'll try to go through a few of them, but I of course won't have the time to go through all of these methods. And this is just a nice way to think about how they're organized. So how do we sort of first evaluate these kind of self-supervised methods? Most people take the ImageNet dataset that I talked about earlier and throw away the labels. And now we basically just look at the images in this case without using any labels. So one of our first works in this area was actually Perl called pretext invariant learning, which showed that you can actually have a very rich class of data augmentations or rich class of image transformations that will learn powerful representations. And in fact, we showed in this case that self-supervised learning can actually outperform supervised learning in a lot of tasks. For example, object detection was one of the sort of landmark tasks that we showed in this work. So for Perl, what we do is we take an input image I and we apply an image transformation T. And so in this case, the image transformation T can actually be about splitting the images up into patches and then rotating the patches. Now we take I and IT and we feed that to a model. And in this case, I'm showing two models, but it's actually the same exact model. So that's why I wrote shared. And what we want is the features that come from both of these paths, from both of these like images to be the same. And to do that, we'll use this technique called contrastive learning. Now, I'll talk about what contrastive learning is, but let's try to understand what is going on in this particular picture. What we're learning is basically that the features are invariant to all sorts of data augmentations. And data augmentations are essentially, say, image editing operations. So filters you can think of, say, on Instagram. And multiple views created by this kind of pretext tasks, which is essentially rotating the image completely, chopping it up into different types of pieces, and so on. So the class of image editing operations that you can perform is actually very rich in this case. And what we showed is that you can actually certain sort of image editing transforms called pretext tasks can actually also serve as these kind of image transformations. And in fact, they serve to improve performance by a whole lot. Now let's try to understand what contrastive learning is, because this is sort of one of the key technical innovations in most of the self-supervised learning work. The idea in contrastive learning is that you have a set of related and unrelated images. So all the blue images in this case are related, all the green images are related, and all the purple images are related. You feed them through a network to obtain features f theta of I, basically for each of these inputs. And now your loss function is going to try to bring together the features of the related images and separate away the features of unrelated images. So pictorial representation is basically that when you have these two images which are blue, which are related, you really want their feature embeddings to be close. And you want to separate away the feature embeddings of unrelated images. So you really want the green images to be far away in the feature space and the purple images to be far away in the feature space. And the same, you can basically repeat the same technique. You really want to pull together the green images while they're separated away from the blue images and so on. Basically, that's how contrastive learning works. And it's a very general framework. You can actually use it for supervised learning or self-supervised learning. And the way that we used it in Perl is basically that we said that all images I and IT are basically the blue pairs, which are related, and any other random image in the data set is actually an unrelated image. And so what we're doing is basically saying that any image I and any transform applied to it should be very, very close by, and features from any other image, any other random image, be it tree or tiger or table, should be far, far away. And this ends up learning really, really powerful features. Now, contrastive learning is just one particular way of doing this thing. There are multiple other loss functions that you can use to enforce this constraint. And we also had a paper earlier last year, which showed a much simpler way of enforcing this kind of constraint. It was inspired by neuroscience, where our main idea was basically that we wanted to reduce the redundancy between features. So rather than getting into the detail, I'll first talk about how we were sort of inspired by neuroscience. So this particular insight actually came from Horace Barlow's efficient coding hypothesis, which says that because a brain has a limited kind of real estate, you have limited amount of space for all the neurons to be in the brain. There is limited amount of energy that these neurons can consume when they're actually processing information. So because of these reasons, the neurons, when they communicate amongst one another, when they use these things called spiking codes, the spiking codes need to be efficient. So neurons should not basically have redundant communication between one another, because in that case, if you have redundant communication, you are kind of wasting the real estate in the brain. You're wasting the amount of energy that is being used and the space that is being used. And so Horace Barlow was really inspired by information theory from Claude Shannon when he was basically coming up with this kind of efficient coding hypothesis. And efficient coding has actually been observed empirically in brains. So for example, in this experiment from 1996, they observed that neural responses in a cat were actually decorrelated. So cats basically seem to sort of respect this efficient coding hypothesis as well. Now, to take this insight from neuroscience, we basically operationalized it into machine learning in computer vision. And the way we did that is basically, this is the same thing where you have images basically being augmented. So you get like these blue pairs which are related. You feed them through a model f theta and you get a representation or a feature. And what we did is we basically, when you get this feature can be thought of as a vector. We compute an empirical cross correlation of this particular feature. And so that will be a diagonal matrix. And all we say is that this empirical cross correlation needs to be as close to the identity matrix as possible. And what this does is basically at the diagonal, you're enforcing that these neurons are actually giving the same kind of response no matter the input image. And at the off diagonal, where you basically are enforcing 0, you're saying that neurons must not be redundant to one another. And just by doing this simple loss function, where all you're doing is setting your target to be an identity matrix, and then basically just subtracting the cross correlation from the identity matrix, you get a very nice loss function, which automatically learns invariant features while sort of preventing trivial solutions. So all of this is great. Self-supervised learning, we saw like 2 ways of doing it in vision. Does it really matter and does it really work in the real world? So to do that, we basically took one of our self-supervised algorithms called SWAV, and we, rather than apply it to a small data set of like hand-picked images, we decided to apply it to random images from the internet, which were not really picked by us. So these images are random. They may contain cartoons, they may contain actual images. We don't know. Basically, we were not enforcing any filtering constraint when we were applying it. So we created this model called SEER, which took 1 billion random internet images with no labels, no metadata. These are just images out there. And we trained a self-supervised vision model on these billion random images. So what does this model do now? Well, for starters, it actually seems to work across all the images that I talked about earlier. If you think about these 2 images, which are like spices from Nepal and stuff from China, the supervised model in the left case seems to think that these spices are actually cleaning equipment, kitchen sink, or shower, whereas the SEER model actually recognizes it correctly as being spices. On the right-hand side, again, we basically see that the supervised model is having a tough time figuring out what this particular concept is, but the SEER model seems to do a much, much better job. So one of the reasons for this is basically because we're able to put in a lot of data into SEER, And this data can actually come from different parts of the world. Because we don't really have this constraint of the data being annotated or data being labeled by people. And so in this case, we're not limited like the supervised model. The supervised model is limited by the amount of data it can ingest because all of the data has to be labeled. And if it comes only from certain parts of the world, it's going to have difficulty recognizing images from other parts of the world. So this already shows us some kind of benefit of self-supervised learning. On other kinds of sort of benchmark tasks in computer vision, we also observed that the SEER model outperformed a supervised model consistently across a variety of different settings. Again, sort of showing the promise of doing self-supervised learning out there in the wild. The other sort of benefit of self-supervised learning has really been that it enables discovery. And this is something which was kind of surprising to us, because we really didn't expect this result when we were working on this paper. So later, like last year, at the mid of last year, we had this paper called Emerging Properties in Self-supervised Vision Transformers. One of the key results for this work was basically that the computer vision model, when we were sort of training it with the self-supervised technique, it automatically learned to understand, like group together pixels which belong to an object. And of course, we never gave it that kind of signal. So in this case, what I'm showing you is an image on the left and what the model recognizes as pixels that belong together. And again, this model has never really seen any single human sort of outlining a bird or outlining a toothbrush and so on. And it is automatically discovering that these kinds of objects actually exist in images without access to any kind of human supervision. So in each of these cases, you can see it's not only that it figures out that there is an object, it also knows the pixels that belong to it. And it's actually predicting pretty accurately which pixels belong to that object, which is very surprising. Even more surprising was that when we were visualizing different parts of the model or different heads in this case, we can observe that it's actually figuring out different objects in the scene. So in the top left corner, there are certain parts of the model that focus on just the, I think that's a turnip or I don't know which particular vegetable, certain parts that focus on the carrot. In the right-hand side, again, certain parts that focus on the sauce or the dip, certain parts that focus on the sandwich. The left, it focuses on the clock tower face differently, the building differently, and so on. And again, on the right, it's focusing on the boat differently than the house. And so a lot of these things really emerge from the model by just doing this kind of self-supervised learning. The advantage of this is basically that for a supervised model, say you decided to collect labels and you didn't have enough time or you didn't have enough like labeling resources, you could say that I just want to collect labels for buildings and I don't want to annotate, say, boats. But what ends up happening is for the self-supervised model, it's actually discovering all of this automatically. So you really are not restricted by the amount of labels that you can recognize. And this actually seems to work also for video. So in this case, we have like a video, we applied Dino per frame to it. And you can see very easily that it's actually segmenting out all the pixels belonging to the object. So that's pretty neat. So this was one example of sort of self-supervised learning that actually applies to discovery. We've also seen that it's not just natural images, it seems to also apply to different domains. And there are like ongoing projects where we're actually exploring this discovery ability of Dino on different image domains. Now I'll talk about how it's not just images, but we can also do the same sort of trick of learning invariant representations, and we can actually go to videos and 3D data as well. And another work we had was basically called Avid, which shows that we can use audio as a source of self-supervision for learning very powerful video features. So the idea in this case is actually very simple. It comes from an earlier work out of Oxford, where the idea is that if you have a video, all videos naturally tend to have recorded sound. What we can do is we basically can set up a correspondence task that given an image and its corresponding audio, that's right. And given basically an image and the wrong video, basically that's wrong. So we can just swap out the audio from one video and we can basically create these correct or incorrect pairs. And in fact, we can actually apply contrastive learning to this particular technique. What we can do is we can feed in the video into a video encoder, get a feature representation for the video. We can feed in the audio to an audio encoder and get an audio representation. And now we can do the same trick of contrastive learning. We can basically say that we want the video feature and the audio feature to be close by. if they come from the same video. And we want the video feature and the audio feature to be far away if they come from different sources, if they come from different videos, basically. And what this really enables us to do is we can actually just now explore this. When we train a model this way, the model automatically learns to recognize which videos are related and which videos are unrelated. And it picks up on both the audio cues and the video cues to do that. So in the top row, I'm showing you a reference point in a reference video. And what we're going to do is figure out what the model thinks are related videos in the audio space, in the video space, and in both spaces. So in the top row is basically a video that is related to the original reference video in both the audio and the video spaces. And in this case, we actually see that it's going to be almost the same video. It's the same video of a person dancing or a person playing a violin or of a train. Now, if the model were to just focus on the visual aspect, it can get confused because a person who's exercising really seems to look very, very similar to a person who's dancing. Or a train, the train station, the model get confused with a fire truck station. If the model were to just focus on the audio, it can again get confused. Say someone was fishing but had the same background music as a person dancing. Or there was a moving boat and the boat was basically making the same kind of sound as a train. But in this case, because the model is using both cues, it's using both the visual cue and the audio cue, it's actually able to figure out which videos are related. And basically by just using this kind of source of self-supervision, all of this again had no labels because all we did was take video and naturally occurring audio and set up a self-supervised task. And on a lot of benchmarks on action recognition, this model ends up becoming the state of the art, both in terms of like the accuracy and also the amount of compute it requires to sort of recognize actions. So in this case, flops. The other sort of emergent property is you can now actually ask questions like, what do pixels sound like? So in this case, what we did was we took a video which had a corresponding audio, and then we asked the model to answer this question. Where do you think which pixels in this particular video are responsible for the audio? And basically the model automatically focuses on the person when it's trying to figure out where this kind of source of sound might be coming through. And we can see similar sort of visualizations when we see people playing musical instruments. The model automatically learns to focus in on musical instruments when you basically give it that sound of a musical instrument. And again, across a variety of benchmarks, these sort of self-supervised models outperform prior work very easily. Now, finally coming to like 3D data, what we can see is we can apply the same trick of doing augmentations to 3D data. So we had a work again last year where we showed that you can take 3D point clouds, which are essentially say something that your phone records, point clouds, which are 3D representations of the world. You can apply different augmentations to these point clouds and again, feed them through a network and ask it to learn an invariant representation by say contrastive learning. And what this ends up doing is basically we can get the same performance on downstream tasks with 2 times the fewer labels because the self-supervised task ends up learning very, very powerful feature representations. So in general, what I've shown you now is that the same principle of learning invariant representations really holds across all visual modalities, across video, across images and across videos and audio, across 3D data. But in each case, when I was doing that, I had to move basically when we were developing these algorithms, we really had to move to different types of model architectures. And this brings me to the last part of my talk, which is not really going to be about self-supervised learning, but about more general flexible models that are actually going to enable, in my sort of belief, the future of computer vision and the future of sort of machine learning models. So these are basically moving towards more and more general models. So one of the sort of drawbacks of computer vision so far has been that when we think of these sort of 3 different visual modalities, image, video, and 3D, they are actually processed by very, very different types of model architectures. And this is very surprising because when we think about humans use the same processing unit, the brain, the same visual sensor to process each of these types of 3 data, right? So when we have images or video, we are able to sort of recognize these things very easily. But for machine learning models, actually, we use very different underlying architectures for each of these 3D modalities. This can create really, really funny situations. For example, if you can even recognize a pineapple, say in images or a pineapple in video, you won't be able to recognize it in 3D until someone gives you 3D supervision, because this 3D model is completely separate from the image and the video model. And so really what ends up happening is, when I talked about labeling earlier, we need labels for each of these three modalities, image, video, and single view 3D separately. So we need enough labels for images and pineapples. We need enough labels for videos and pineapples. And we need enough labels for single view 3D and pineapples, which seems to be really weird, because we should be able to share this kind of information across these three modalities. They are very related. They are all visual. So in work that we just put out like publicly last week, we designed a single omnivorous model. So this single model can actually ingest image, video, and single view 3D and process them with the same parameters. And so you can think of this, the reason we decided to call it omnivore is basically the earlier models are very picky eaters. They can only eat images. If the image model cannot really eat video, the video model can't really eat 3D and so on. Whereas the omnivore model is not really picky. It can eat image, video, or single view 3D. And so this work is out there publicly on GitHub, like with the coded models. The sort of key idea in this case is that we can take input images, video, or 3D, and we can feed them through a single model. And we really leverage the transformer architecture to do this. So to basically feed them into the same model, what we do is we take the input image, we split it up into a bunch of patches, and we do the same operation for, say, the video, where we split it up into a bunch of patches. And the same thing for actually video, single view 3D. We can split the image and the depth into separate patches. And now we input these patches into the same model. And so for the model, it's actually able to just operate on these patches, and it can be kind of agnostic to where these patches are coming from. So if it has lots of patches and we just tell it that these patches are coming from the temporal dimension, it can actually do temporal reasoning for video. If we tell it that these patches are coming from the 3D part, it can actually do 3D reasoning as well. And lo and behold, actually one of the surprising results for this work was that these omnivorous models actually outperform these modality-specific models on a bunch of these different tasks. So in this case, I'm showing you ImageNet, which is a very sort of classical image recognition task, Kinetics, which is a very standard video recognition task, and Sun, which is a very standard single view 3D recognition task. And of course, for each of these tasks, there are specific models that were designed. There is like image-based model, there is a depth-based model, and so on. And these models can only apply to that particular data set, and they of course don't work on the other data sets. Whereas in our case, the omnivore model, the same model works on all three data sets. And in each case, it actually ends up outperforming the modality-specific models. So essentially, rather than training three models, you can actually train just one model. And now, coming back to our original motivation, what we really wanted was, if we were to recognize a pineapple in images, we want to be able to recognize it in 3D as well. But when we were training this model, we didn't really have this kind of supervision. So what we did was we actually just concatenated basically image supervision, video supervision, and 3D supervision. And these three data sets that we concatenated had no label overlap. So ImageNet was really focused on basically recognizing objects in the world, which can be dogs, cats, and so on. Kinetics is really focused on human actions. So is a person playing golf? Are they like throwing something? Sun is really focused on indoor objects. So like chairs, tables, something that is basically taken indoors, nothing to do with the outdoor world. And we never had any paired observation. We never had a single like image from ImageNet for which we had the 3D, because these three data sets were collected completely independently and have different sizes. But one of the surprising property is that because we are training the same model, the same parameters, this model automatically learns to share representations across these three modalities, across images, videos, and 3D. So this is an emergent property. The model is not trained to do this, but it automatically learns to do this because of the way we set up training and because of its architecture. And so on the left-hand side, we have an input image, say a pineapple. What we can do is we can actually take that image and we can retrieve whatever looks as the closest depth to that particular image. And this model ends up looking at pineapples, recognizing pineapples that it has never really seen. It has never seen any depth maps for pineapples, but it's actually able to recognize those. It can retrieve single view 3D or even videos for that pineapple. So one simple way to apply this is basically that on the left-hand side, when I took that input image of a pineapple, if I assigned it the label, or if I got a label for it called pineapple, now the model can automatically recognize all the depth maps as pineapples, all the single view 3D that it retrieved as pineapples, and all the videos of pineapples as well, with just a single label being applied to the image. It can basically recognize the entire row. And the same thing holds for all of the concepts that I'm showing later. So for the golf cart, it can basically recognize golf carts in 3D. It can recognize videos of golf carts. The same thing for boats, the same thing for Halloween pumpkins. And so essentially, our thinking is that by modeling together these three modalities, these visual modalities, which really are very, very correlated, very, very related to one another in a single model, we should be able to train more efficient representations. And if we were finally to apply them to some kind of application, we require fewer labels, because we can actually just label one modality, whichever is easiest, and then automatically the sort of supervision transfers to other modalities. So that brings me to the end of my talk. I think I have about 15 minutes, so I planned for 45. I guess I finished in time. Thank you so much. Today I talked about like these two lines of work: self-supervised learning and general models. All of the code for all of the research that I talked about is public. All of the papers are public and accessible, like at no cost. And these are the links on GitHub for them.
Thanks, Ishan. That was really cool and state of the art. Thanks for sharing these. We have